Now that we've seen how we can work with matrices and manipulate matrices, even do our matrices on our calculator, now it's time to finally look at some applications of matrices. The first application we're going to take a look at today is more of a fun one. It deals with cryptography. Cryptography is the study of codes, coding things. So we could send secret codes to other governments or just across the hall, however you want to do it. But we can use matrices to make a very hard-to-crack code by using what is called a key matrix. We're going to multiply a message by a matrix key on the left to code the message. Then, when somebody receives the coded message, the only way they can decode the message is if they know what the key's inverse operation is. In other words, to decode the message, they will multiply by the inverse key on the left. So here's what I mean by that. First, we have to get every letter needs to be converted into a number. So you can do this all sorts of ways. For the sake of the cryptography we're going to do a really basic code where we list the letters A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, and Z. And we'll just really quickly assign the numbers 1 through 26 to each letter. So A is the number 1, B is 2, C is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. And then if we need a space or any extra characters, we'll use 27 for the space to separate words. So let's code a message. We are going to code our course name. We are in finite math, and we are going to code it using the key A equals 2, 5, 1, 3. So because our key is a 2 by 2 matrix, we are going to make columns of 2 out of our code, our message. So in columns of 2, we're going to have Fi, the next matrix, Ni, and then the next matrix, Te. Then we need a space to separate the word, M, A, T, H, and then we seem to need one extra character to finish out this matrix, so we're going to do a hyphen. So we make column matrices to match the key. So if it was a 3 by 3 key, we would make columns of 3. Then what we're going to do is we're going to convert these into their numbers. So F is the number 6. I, we see, is the number 9. N we see is the number 14. I, again, we see is still the number 9. T, we see is the number 20. E, that's the number 5. Then we need a space. We said space would be 27. M we see on here is 13. A is the number 1. T, again, is the number 20. And H is the number 8. And again, space is 27. Then what we're going to do is we are going to multiply the key, which was that matrix A, 2, 5, 1, 3, times each of these matrices, times 6, 9, times 14, 9, 2, 5, 1, 3, 2, 5, 1, 3 is 25. Then 2, 5, 1, 3 times 27, 13. 2, 5, 1, 3 times 1, 20. And finally, 2, 5, 1, 3 times 8, 27. And this is going to give us our coded message. Using our calculator to help with the multiplication, just to make it faster, you can multiply it by hand if you wish. We're going to hit second matrix. We're going to go over to Edit, and we're going to program the key in. It's a 2 by 2 key. 2, 5, 1, 3. Then we program the first matrix in to matrix B. It's a 2 by 1 matrix, 6, 9. And then I'm going to hit second matrix. We'll grab matrix A, the key, and multiply it by matrix B. And when we do, we get 57, 33. 57, 33. Now we'll do the next matrix. Second matrix, we just have to change matrix B. It's still a 2 by 1 matrix, but this time it's 14, 9. Second quit. And what's nice here is we're going to do AB again. So instead of having to type AB again, we're just going to hit Enter one more time. And it retypes what we typed previously, this time giving us 7341. And then we keep going down the line. Matrix, go over to program our new matrix B. It's still a 2 by 1. This time we're programming 25 in. Second quit. Hit enter again to repeat the previous operation. 65, 35. 65, 35. And we do it again. Our new 2x1 matrix this time is 27, 13. And hit enter again, this time giving us 119, 66. Two more to go. Changing matrix B again. It's still a 2x1. This time it's 120. Hit enter again. 102, 61. And finally our last one. Changing matrix B this time. It's still a 2x1. This time it's 8, 27. Hit enter one last time, and we get 151, 89. And so when we write out our coded message, we just list these numbers. 57, 33, 73, 41, 65, 35, 119, 66, 102, 61, 151, and 89. And that becomes our coded message. The only way to decode this message is if you know what the key was to begin with and can find its inverse. So let's look at actually decoding this message. To decode the message, we first have to find the inverse of the code of the key. Fortunately, we've already got A in our calculator, and it can tell us what the inverse of A is. So we grab matrix A and hit the inverse button and hit enter. The inverse key is 3, -5, -1, 2. 3, -5, -1, 2. That's the matrix that can be used to decode this message. And so in much the same way, we're going to multiply the inverse on the left, 3, -5, -1, 2, times each of the elements in our message. And when we do that, we have to pair them up because our inverse is a 2x2, so we need columns of 2. Very similar to how we coded the message, 57, 33. 3, -5, -1, 2 times 73, 41. 3, -5, -1, 2 times 65, 35. 3, -5, -1, 2 times 119, 66. 3, -5, -1, 2 times 102, 61. And finally, 3, -5, -1, 2 times, the last one was 151, 89. So we're going to multiply these out. I'm going to put the A inverse into matrix A, and here's kind of a nice trick you can do is if you want to take a current matrix like we have on the screen and stick it into the new matrix A, we can hit the store button right above the on key and then select matrix A. Second matrix A. And what this is going to do is take the answer just above, and it's going to replace the old A with what's right above. So now when we type matrix A, we're going to get that 3, -5, -1, 2. So now we can just go in and program the B matrices, the 2 by 1 matrices. And the first one is 57, 33. Second quit. And now we can select matrix A times matrix B. When we hit enter, we get 6, 9. Reprogramming matrix B then for the next one. It still is a 2 by 1 matrix, not a 21, but a 2 by 1. There we go. And we have 73, enter, 41, enter, second quit, and then I can hit enter again one more time, and I get 14, 9. Now for the next one. Second matrix, edit the 2 by 1. This time it's 65, 35, and quit and hit enter again, 25. Halfway done. Second matrix, over to edit. Edit B, the 2 by 1 matrix, 11966. Hit enter, we get 2713. Two more times. Two by 1. We've got 10261. Second quit. Hit enter again. 120. And finally, the last one, a 2 by 1 matrix, 151, 89. Second quit, enter, 827. And you'll recognize these as the column matrices we started with at the beginning. Now all we have to do is decode them, remembering that code we had A, B, C, D, E, F, G, H. My H has got a hole in it. There it goes. I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z, and space. And we just numbered them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, and 27. So now we just crack the code by looking at the list that we have above. We've got the number 6 to begin with. 6 is an F, followed by 9, which is an I. 14 is an N. 9 is an I again. 20 is T. 5 is E. 27, that's our space, so we're going to have a space to start a new word with 13, M. 1 is A. 20 is T again. And 8 is H, followed by a space that finishes us out, and we have decoded our code. So that's kind of how you can use cryptography, coding messages with matrices, and you can see where you can make this really difficult to decode by doing variations. You could move the alphabet around so the numbers are all in different places, so only you and the code breaker know what the code is. You could do a 3 by 3 matrix, which is harder to find the key. You could do columns and rows, so you've got 2 different ways to interpret the key. So great way to encode a message, and makes it seem quite random and very difficult to crack the code. Kind of a fun application, but most of us in this class are more on a business track of things than a code breaking track of things. So let's reel it back in and let's talk a little bit of business. I want to talk about, and I'm going to pronounce this guy's name wrong, so if someone wants to come to class and tell me the correct way to spell this economist's name. I'm going to call him Leontief. I'm not sure if that's correct, but he's one of the great economists of the world. He has won the Nobel Prize. He's had several students that have won the Nobel Prize based on his training in economics. Great contributor to the economy. And he developed what are called Leontief models, which basically divides the economy into sectors. And each sector produces goods for themselves and for other sectors. So this is the idea that the farmer sells food and corn to other people, but he also keeps some of the corn for himself. So he keeps some of his economy or some of his goods, and he produces goods for other people as well. So the economy is split into sectors, using some of it and giving some of it to other sectors. Now we're going to look at a very simplified version of this to start off with, called a closed model. And in the closed model, all goods are consumed by the producers. There is no outside demand on any of this work. Now, when we set this up, we're going to set up a matrix that's going to describe what's going on. The columns are going to represent the producers, what they produced, and the rows are going to represent what they consume, or we'll use the word use. So you produce something and you use something. And what's important here is that that in order for this all to be in equilibrium and for this all to balance, the amount paid must equal the amount produced. So if we have a farmer and a tailor and they're exchanging food for clothes, the exchange should be equal. The amount paid should cover the amount produced. That's a fair equilibrium balance. And now if we look at that in terms of matrices, the amount paid, x, is going to equal the amount produced. And the way we calculate the amount produced is if we call this matrix above matrix A. The matrix that shows produced and consumed is multiplied by the produced, and that should equal the amount paid, the same amount. Well, let's play with this algebraically a bit. Let's subtract ax from both sides. That's equal to 0. We have a common factor of x. X is on the right of the A, so because these are matrices, we have to preserve the side. So we'll factor x out on the right side. X divided by x is 1. In terms of matrices, 1 is the identity matrix. 1's down the diagonal, minus A equals 0. So the way we're going to find out how much everybody should be paid is we're going to look at this matrix I minus A times x has to equal 0. It's going to set up a system of equations for us that will have an infinite number of solutions. So we won't be able to solve this with the inverse method, but we will be able to solve this using reduced row echelon form and then interpreting the result in terms of the infinite number of solutions. It probably makes best sense when we look at an example. We're going to come back to this equation. This is an important one. I minus A times x equals 0. Let's say we have an electrician, a carpenter, and a plumber. Who do work on all 3 houses. These 3 buddies decide, hey, I'm an electrician, I can help you out. You're a carpenter, you help me out. I'm a plumber, you help me out. And we'll exchange the work around, and we'll see how much everybody owes everybody at the end. So when all is said and done at the end, the electrician documents electrician. That's supposed to delete. There it goes. Spends 30% of his time on his house. 45% on the carpenter. And 25% of his time on the plumber's house. The carpenter spelled with a T, I think, right? The carpenter spent 35% of his time on his house. %40 of his time on the electrician. And 25% of his time on the plumber. Finally, the plumber's time card shows that he spent 65% of his time on his house. Actually, let's make this one a girl. We don't have any girls yet. On her house. 30% on the electrician. And 5% on the carpenter. The group felt originally they should each get paid $550 based on the work in the end. What should each be paid? Based on the work, what should each one of these guys be paid based on how much time they spent on their own stuff versus actually working for the other guys? Well, to do this, we're going to set up our A matrix. That shows the amount produced and the amount used by each of these sectors of our mini economy. So we have an electrician, we have a carpenter, and we have a plumber. Each one's producing goods and each one's using goods. The electrician, the carpenter, and the plumber. Produced. The amount produced is what the person actually did. So what the electrician did goes down the column. What the carpenter did goes down the column. What the plumber did goes down the column. Columns are for what you actually did, what you actually created, what you actually produced, to be used or sold. So when we see that the electrician spent 30% of his time on his house, the electrician produced 30% or 0.3 of his work that was used by the electrician. Similarly, he spent 45% on the carpenter. So the electrician produced 45% of his work that was used up by the carpenter, going down the column, and finally 25% for the plumber. Now the carpenter is going to give his work, his production, down the center column. He spends 35% on his own house, so 35% on the carpenter's house. He spends 40% of his time on the electrician's house, and 25% of his time on the plumber's house. The plumber's work then, on the next sentence, he spends 65% on his own house. So 0.65 on his own house. Her own house, sorry. 30% on the electrician. And 5% on the carpenter, 0.05. So, what we need to find is that equation, the identity minus the A matrix times x equals 0. So the identity, that's 1, 0, 0, 0, 1, 0, 0, 0, 1 minus the A matrix, which is 0.3, 0.4, 0.3, 0.45, 0.35, 0.05, 0.25, 0.25, 0.65. So this is the parentheses I minus A. And that's going to equal, could do it on the calculator, but it's probably really easy just to do on our own. 1 minus 0.3 is 0.7. 0 minus 0.4 is negative 0.6. 0 minus 0.3 is negative 0.7. Oh, no, it's not. 0 minus 0.4 is negative 0.4. 0 minus 0.3 is negative 0.3. 0 minus 0.5 is 45 is negative 0.45. 1 minus 0.35 is 0.65. 0 minus 0.05 is negative 0.05. 0 minus 0.25 is negative 0.25. 0 minus 0.25 is negative 0.25. And 1 minus 0.65 is positive 0.35. When we do this subtraction, you will notice that the only positives are up the diagonal, where there were ones that we were subtracting. So now we've got this matrix times x equals 0. This matrix we just found times the variable matrix equals 0. We're going to make this into an augmented matrix then. Because x, that's the variable ECP, how much the electrician, the carpenter, and the plumber deserve, we're going to augment this matrix with the solution 0 afterwards. So 0.7, negative 0.4, negative 0.3, augmented with the solution 0, negative 0.45, 0.65, negative 0.05, augmented with 0, negative 0.25, negative 0.25, 0.35, augmented with 0. And we're going to solve this system. Because this system will always have infinite solutions, we cannot use A inverse B, but we can use reduced row echelon form to get the solution. So let's program our matrix in. We're going to edit. Might as well put it in for A here. This time we've got 3 rows and 4 columns. 0.7, negative 0.4, negative 0.3, 0, negative 0.45, 0.65, negative 0.05, 0, negative 0.25, negative 0.25, oops, not negative this time, just 0.35, and 0. Second quit. Now I could just grab reduced row echelon form of matrix A, but I like to make sure I typed it in correctly. So I put matrix A and hit enter just so I can look at it on my screen, make sure all the values are correct, and as I cross-check it all looks good. Scroll over to make sure there's all zeros at the end. And so now we'll do the math with it. Second matrix, over to math, and reduced row echelon form of the previous answer. Enter. Looks like this. Those ugly decimals aren't going to be helpful, so we'll go math, fraction, so we can see it better. And there is our reduced row echelon form. Notice all zeros on the bottom, implying there's infinite solutions. We got 1, 0, negative 43 over 55, 0, 0, 1, negative 34 over 55, 0, and the last row was all zeros. Remember, in the order of our variables here, it was ECP, electrician, I'm going to say, go down the columns, electrician, carpenter, plumber. So if we were to rewrite these, remember what we do with infinite solutions, rewrite these as equations. We've got 1 electrician minus 43 over 55 plumbers equals 0. We've got 1 carpenter minus 34 over 55 plumbers equals 0. And then finally we've got nothing for the plumber. That's where we introduced our dummy variable. Nothing for the plumber, so we say the plumber is T, and we're going to replace those plumbers with the T's as we solve each equation. So the electrician is equal to 43 over 55 times the plumber, which is T. C is equal to 34 over 55 times the plumber, which is T. And the plumber then is just T. So how much money does each deserve to be paid for their work? Well, remember, they each originally agreed that the work they were doing would pay $550. That is what's going to be used for our T to find out the fair amount of pay based on their work. So the electrician gets paid 43 over 55 times 550. The carpenter gets paid 34 over 55 times 550. And the plumber gets paid 550. You can do this math on the calculator, or you can do this math almost mentally, because 550 over 55 is 10. So that makes it really easy to determine that the electrician should be paid $430. The carpenter should be paid $340. And the plumber should be paid $550. And then they would have a fair amount of pay, input equals output, for their work. So that's how the closed model works. The closed model works by finding their matrix for produced and used, finding what that I minus A is, and solving that matrix, that augmented matrix. However, in real life, you don't just produce goods for yourself and your buddies. You produce goods to be sold on the open market. So the more realistic model would be the open model. The open model must also satisfy outside demands. And those outside demands, we're going to use the column matrix D to represent the amount of demand also put on the economy. Again, the amount paid for their work must equal the amount produced, but this time we also plus must satisfy the demand, the external demand, you might say. So the amount paid, X, has to equal the amount produced, which is the matrix times the X, but also plus the demand. So let's solve this equation for the variable. Let's again subtract AX from both sides. That's going to equal the demand. Again, we've got a common factor of X that we can factor out on the right side, because it's on the right side of A. X divided by X is the identity, minus the A matrix equals the demand matrix. To solve this for X, we just have to multiply by the inverse of what's in parentheses, the inverse of the I minus A on the left. So we're going to do it on the left here. And that gives us X is equal to I minus A inverse times the demand. This is another key equation we need to know for the closed model. This is really nice because this one has one specific solution. It's not infinite. There is one solution. We can actually find this on our calculator real quick. We'll just program in the identity. We'll program in matrix A, and we'll program in matrix D, and then ask the calculator to calculate what the appropriate pay is going to be for each sector of the economy. So let's look at an example. Let's go back to our electrician, carpenter, and plumber. Of what the electrician produces, 10% is used by himself, 20% by the carpenter, 15% by the plumber, plus the consumer uses $10 billion. Okay, we're probably talking more than just one electrician. Maybe it's a group of electricians at a firm offering a firm of carpenters and a firm of plumbers, and the firm also gives the customers $10 billion worth of service. That $10 billion sounds more like we're talking about an economy, though, than just $10. Of what the carpenter produces, $30% is used by him, 10% by the electrician, and 25% by the plumber. Plus the consumers using $15 billion. Of what the plumber produces, $15% is used by him. Or we said the plumber was a her, sorry, used by her. 25% by the carpenter, and 10% by the electrician. And $12 billion by the consumer. Oops. Get it all on the screen here. There we go. So A is going to be our demand matrix. Actually, let's make sure we have room to show what is produced and used by the electrician, carpenter, and plumber. The electrician, carpenter, and plumber. Same idea as last time. Going down the columns, the electrician produces 10% used by him, 20% by the carpenter, and 15% by the plumber. We'll do the demand externally in just a minute. The carpenter produces 30% by him, 10% by the electrician, oops, 30% by him. That's 0.30 on the carpenter, 10% on the electrician cell, and 25% by the plumber. Plus consumers using 15 billion. Of what the plumber produces, 15% is used by her. So the plumber uses 15% of her own work, 25% by the carpenter, and 10% by the electrician, being careful to make sure we get everything used by the right sector. So that part's pretty similar. That's our A matrix. We also have a demand matrix, which is a column matrix that shows the demand on the economy in the same order by the electrician, carpenter, and plumber. The electrician's demand was $10 billion. Continuing to read through, the carpenter's demand was $15 million. And the plumber's demand was $12 million. We're also going to program on our calculator an identity matrix that matches with identities in threes. We need a 3 by 3 identity matrix. So we'll program that into our calculator. So in our calculator, we've got A, the internal use, the closed model version of what's being used by all three industries amongst each other. We'll have a D matrix, that's the external demand on each of the three sectors of the economy. And finally, we'll have an identity matrix, which is going to be used as we run the calculation on our calculator to get that important equation, I minus A inverse D. So we'll bring out our calculator, and let's first program matrix A. Second matrix, we'll go over to Edit A. Now A is a 3 by 3 matrix with 0.1, 0.1, 0.1, 0.2, 0.3, 0.25, 0.15, 0.25, 0.15. Second quit. Moving the calculator over a bit to see the D. So we'll go to second matrix. We'll go over to Edit. And I like to match the letters. We've got lots of matrices to work with. Since this is the demand matrix, I'm going to put this in for D, the demand matrix, which is 3 rows and 1 column. 10, 15, 12. And we'll go second quit. The other matrix we wanted to put on there is the identity matrix. Second matrix. And I'm going to scroll down all the way to the I for identity, just because I've got lots of letters. I might as well use I to always represent my, whoops, we're programming it, not using it. Second matrix, Edit. Scroll down to I. And I'm going to make a 3 by 3 identity matrix, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. So now we've got A, D, and I programmed in the calculator. So I can just type in this formula, parentheses I, second matrix, we'll scroll down to I. Also might help to make it quicker, I could have just hit the number 9, seeing that 9 is the identity matrix from the top. Either way would work. Minus matrix A, second matrix. A is number 1. Close the parentheses. And then we want the inverse of that, so we will hit the inverse button, times matrix D. Second matrix. Matrix D is number 4. And so I can see I'm actually typing in my calculator just like the formula, I minus A inverse times matrix D. Hit enter. And it gives me these values. And those are in billions, so we're just going to round everything to billions. 18.31 billion. 18.30, what's it? 18.32 billion. 36.72 billion. And 28.15 billion. And so that's what each sector, the electrician, carpenter, and plumber, should make in this economy. The electrician's making $18.32 billion. The carpenter sector is making $36.72 billion. And the plumber sector is making $28.15 billion in this economy. So that's how the open model works. It's a lot more realistic. You could see how this will be extended to hundreds of sectors in the economy, especially with calculators doing all the work, to figure out how much money each sector can expect to make under the current economic conditions. So how we did the open model is we first identified the internal exchange matrix, if you will, how much is produced and used by the sectors amongst each other. We determine the external demand, and then we calculate on the calculator I minus A inverse times the demand to find out the amount each sector is going to make. The cryptography is a lot of fun. What I care about most in this lesson are the Leontief models, so please take a really good look at those. That's what we're going to focus on in class tomorrow, and please come with any questions you might have. See you tomorrow.